Okay, so one of these guys. Because it's an equation, and you're going to end up doing the derivative of both sides anyway, you know what you can do to make your life a little easier is you can make that negative go away. So I might actually do that. I might actually just take a second and rewrite this thing like this. And then I have one less negative to have to distribute through things when I'm done. Okay, and now I'm going to do the derivative of both sides. So the first part's easy, right? Then this part is going to have a chain rule inside of a chain rule. Or a product, well, it's going to have a chain rule inside of a product rule inside of a chain rule. There we go. That's what it's going to have. So let's do the outer function first, right? To the power of 4 times the derivative of what's inside the bracket. I think I'll open up a square bracket for this. So the derivative of, well, the 4 has a derivative of nothing. That's nice. But this thing here is yet another chain rule. So it's going to be 6 times, and then I'm going to have this as the derivative of, so I'll do 5x to the, or no, how about I do that right, eh? Sorry, I meant to say 6x to the 5, y to the 3. So that's the derivative of the first thing times the second, plus the derivative of the second thing times the first. And of course, the derivative of 4 is just 0. So, yeah. Oh, still an equation. So now my goal is to isolate this equation for this variable, right? That's what I have to get to at some point. So let's see what we can do. I think factoring is going to be our friend here. So I am going to, let's see, what can I factor? 12x I'm just going to leave as 12x for now. But I notice that I have a 6 here. I have a 6 here. I have a 3 here. So I can factor out at least a 3. So this is now 15. Oh, wait, no, I can't. Sorry, I just realized this 6 is to the power 4. No, I'm going to leave that alone. So this, I'm going to factor a 3 out of those two things. That's about all I can manage. And then I'll just put that out front here. So that's now 15. This, however, I'm just going to leave alone, at least for now. Yeah, I don't think there's anything I'm going to be able to do with that. Meanwhile, over here, is there anything else I can factor out? I could factor out x to the power of 5, because this has an x to the 5, this has an x to the 6. So I'm going to factor out an x to the power of 5. I can factor out a y squared. And then what does that leave in this bracket? Okay, I factored out a 3 from these two things, so this is now still, and there was already a 6 out here. You know what? Why don't I take this 6 and multiply it by the 5, which I already multiplied by the 3. So how much is 6 15s? 6 times 60 and 30, 90? Let's make that a 90. So there, that took care of this 6. And I've already factored a 3 out of these two things. So this is now 2 and y plus x dy by dx.
We would like to acknowledge with respect the treaty one land upon which it was completed and Untitled School Division.
Okay, I'm recording again. Okay, let's finish off this question here. See if we can get the same answer as the back. All right, I think we're about as factored as we can be, I guess. Yeah. So let's see, what else can we do with this mess? Not too terribly much, I don't think. Okay, I'm going to move the 12x to the other side. So I have, again, 90 times x to the 5 y squared times 6x to the 6 y cubed plus y 4 to the 4 times 2y plus x dy by dx, right? All of that is equal to negative 12x. So there's step 1. Step 2, I'm going to take all of this stuff and divide it under the negative 12. So 2y plus x dy by dx is equal to negative 12. Oh, sorry, there's an x on that. I forgot the x. All over this mess. So 90x to the 5y squared, and then times 6x to the 6, y to the 4, or y to the 3 plus 4 to the 4. I can do a little bit of simplifying and then move over this 2y. And so let's see. How about this x goes into here, leaving that a 4. What's the greatest common factor of 12 and 90? I want to say it's 6, right? 6 15s and no? Yeah, it's 6. So that makes that a 2, and that is a 15. And then, okay, so then I'm going to do my last two steps. My last two steps are to move this to the other side and make it a subtract, and then divide by x. So that's going to be a negative 1 over 15. And since I'm dividing this thing by this x, that x to the 4 becomes an x to the 5 again. And then a y squared, and then the rest of this thing. Notice this is the thing kind of trapped in a bracket to the power of 4. I don't feel like expanding it or anything. Then minus the 2y over x. There. I can't look at that and think of anything else that I want to do with it. So is that anywhere near what they have for an answer? I can't, let's see, do I have the answer key here? What number was this? Number 3. Oh my, okay, so negative 2. I have, this part I have exactly right. Oh yeah, it is a 2, I'm sorry. Why did I cancel this down to a 1? You can see my little 2 right there. I just wrote it down wrong. There. So negative 2, 15, x to the 5, y to the 2, 6, x to the 6, y to the 3, plus 4 to the 4. Yep, that's exactly the way they have it. So there we go. Question? Go back to the, how did I go back to the x to the 5? Because my last two steps were I had to move this to the other side of the equation by subtracting. Then I divided both sides of the equation by x. And when you divide this thing by x, there's another x in the denominator, so x to the 4 became x to the 5 again. So that's how I did that. Okay? All right, so there we go. For those of you just joining us, since we were waiting on people to get here, I thought I'd just take a homework question. But I do want to do a couple more related rates problems, and I want to refresh you on something that you might have learned in grade 9, but I taught grade 9 for a lot of years. Some years I would get to this topic, and some years I wouldn't. How's your similar triangle knowledge? Okay, I'm looking at a lot of blank stares, so it's a good thing we're going to talk about it today. Actually, the first example we're going to do, I don't even need that. And, oh, sorry, didn't mean to do that. Actually, maybe the first thing I'll do is I'll go back to a question I got yesterday at the end of class when I'd already shut off the video and a whole bunch of people at home had already left. Actually, I think all the people who had to go to music had already left. But it was a really good question, so and my fault for maybe not making this super clear. Somebody asked me, hey, back in example 0, how can the rate of areas changing be a constant? And I hope I didn't, I guess I must have created the impression that I think that the rate of change of the circle in this problem is always 6 pi. Oh, no, it's not. The rate of change is changing, right? The actual size, the area of the circle is growing, and the rate at which it's growing is changing every instant. That's what makes this calculus. That, at its heart, is what calculus is. It's variables that are changing at a rate that you still have to try to solve for. This is the rate of change at the point when the radius is 3 centimeters. And the little animation that I showed you really kind of makes that clear because they do a nice job. They graph it. Here, I'll put it back up if I can find it. There it is. Here's that rippled circle thing. Oops, there we go. So when I drop the pebble, right, check it out. See how that red line is changing its slope all the way, right? The actual change in the area, the rate of change of area is itself still a curve, which means the rate of change is changing, which makes sense. That's what makes it a calculus problem. Okay, so the only, at time is 3 in our problem, we found the slope right there, and the slope happened to be 6 pi. But the slope would be bigger the further I go. You can see that in the arithmetic too, right? If I plugged in a bigger radius, I'd get a bigger rate of change for the slope. Does that make sense? So all of these problems share this in common, right? Well, not quite all of them, because the very next problem, was it the next problem, was the ladder? No, very next problem after that. The one with the ladder has 2 different variables that are changing, but one of them is changing constantly, right? The mother is pulling at a constant rate of 3 feet per second, but the top of the ladder is falling and it's accelerating as it falls. So its rate of change, which is speed, is itself changing. And of course, a changing speed is an acceleration. So this one has 2 variables. One of them's changing at a constant rate. The other one's changing at a changing rate. Today we'll look at examples where we have 2 variables that are both changing at changing rates. So that's where we move to today. So can everybody look at example 3? And let's read it first. The height of a cylinder is increasing at 7 meters per second, and the radius is increasing at 3 meters per second. And what we would like to do is find out how fast the volume is changing when the cylinder is 5 meters high and has a radius of 6 meters. Again, it's the change in volume is not a constant. So we just want that snapshot. We want that instantaneous slope of how much it's changing at this point when radius is 3 and, or sorry, when volume, or radius is 6 and height is 5. Okay, so let's quickly sketch a cylinder. Okay, and of course a cylinder has a radius and a height. Okay, now let's kind of take inventory of our givens. We're told that we know that the height of the cylinder is increasing. So the change in height over time, with respect to time, or the change in height divided by the change in time, the rate of change of the height is 7 meters per second. The change of radius over time is 3 meters per second. So this thing's getting taller much faster than it's getting wider. So it's getting taller, but it's also getting skinnier. Then we know that we have a point where R is 6 and H is 5. Both of those are in meters. And what we're being asked to find is we'd like to find the change in volume over time. So there's the organization of all our information. We got a picture. We can visualize this. You can kind of, I don't have a little animation for this one, so you just have to use your imagination. Imagine that this height is getting taller at a rate of 7 meters per second, and this radius is expanding at only 3 meters per second. So it's getting taller faster than it's getting wider, so it's getting skinnier. But it is getting bigger, right? Its volume is constantly increasing. And it's not increasing at a constant rate. I shouldn't use the word constant there. And I'm going to have to find a formula that relates volume to radius and height. So some of you might remember this from junior high. Volume of a cylinder is the same as it is, whoops, hang on a sec, is the same as it is for any prism. It's the area of the base that it sits on times how tall it is. So I need to find the derivative of this. So let's find the derivative. So the derivative of velocity with respect to time. So I'm taking this entire equation and doing its derivative with respect to time. So the derivative of velocity with respect to time is going to equal to, well, the pi is just a coefficient, so we can kind of ignore that. And then we're doing the derivative with respect to time of r squared h. And that's going to take both implicit differentiation and a chain rule. Okay? So, derivative with respect to time, the thing we're actually looking for, is pi times, okay, so this is a product rule. So it's going to be the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. Everybody get the logic on that? Oh, hang on. Any questions on how I got to this point? Okay, now that I'm at this point, I can actually kind of go back and look at my givens and plug a bunch of stuff in. I know that I'm looking for the derivative here, the slope, when the radius is 6, when the height is 5, and I was given those two rates of change, which in this case are both constant. Question?
Could you just repeat, like, which one was, like what you just...
How did I get to this step?
Yeah.
Okay, so let me use the highlighter. This is a product rule, right? So how do you do product rule? I did the derivative of this thing here, right? And then times the other thing, plus the derivative of this thing here, right? Did you see it now? Because remember, derivative of just a variable, the variable becomes its power of 0 and it becomes 1. But then I still have a dh dt, right? Because I'm not actually doing the derivative with respect to h. I'm doing it with respect to t. Okay? All right, so let's plug in numbers now. The derivative of the volume with respect to time is pi times 2r. Okay, so r we know is 6 meters. So 2 times 6. The derivative of r with respect to t is 3 meters per second. Plus r squared, so 6 squared, times dh dt, which they told us was 7 meters per second, right? The rate at which height is changing. And okay, can you tell what unit you're going to be in? Because again, that's always a nice way to know if you're getting, what unit should you be in? You're talking about volume per second. So what unit should you be in? You should be in meters cubed per second. And think about this. This is meters per second times meters times meters. So there's your cube, right? Question? Yes, but you'd have to change that because there is not 1 liter in a meter cube. There's 1,000. So you'd have to use a conversion factor of 1,000 liters per meter cube. Think about how big a cubic meter is. Like here, those of you at home aren't going to be able to see this very well, but a cubic meter is a cube where that's one of the edges. So length, width, depth, right? Like think about that. That's a corner that I just made. So that's 1,000 liters. So I don't know that I'd want to go to liters because I'd have very big numbers to deal with. But you could. You just have to use a conversion factor. Okay? All right. Let's get a number for this. 6 times 6 is 36. 36 times 7. 36 times 7 plus, I actually punched this out already. I think I get 432. So 432 pi centimeters cubed per second. And again, where did the centimeters cubed per second come from? Well, this number here is centimeters per, or is it centimeters or is it meters? Meters. It's not centimeters. Sorry, it's meters. That's why I was playing with the meter stick a second ago. Ha ha. This number was meters, hold on a sec. This was meters per second, and this is meters squared. So that's where meters squared per second comes from. Okay, what's your question? Where did the h go? H is right here. It's the 3. Isn't it? Or did I forget? Oh, sorry. I forgot to write it down. You're right. I lost h. H, what is h? H is 5. There we go. Here, let's use more colors. Good eye. Oops, that's supposed to be a different color. There we go. So this part here is here. There we go. So there's where my h went. Sorry about that. And multiply all that out, you should get 430. Or multiply all this and add it, you should get 432. Maybe I should double check it since maybe I did miss the 5 when I punched this through. 12 times 15. Add 36 times 7. No, I had it punched right. I just wrote it down wrong. It's 432. Okay? All right, I started with that one because that's my easier example today. The next one gets a little bit hairier. Water is flowing into a conical tank at a rate of 5 meters cubed per second. And again, boy, that'd be a heck of a lot of water if you think about how big a meter cubed is. We just talked about that. If the radius of the top of the cone is 2 meters, the height is 7 meters, and the depth of the water is 4 meters, then, that should be then, not they, then, how fast is the water level rising? Question? Yeah, we won't expect you to remember your junior high shape formulas. Any formulas you need we'll give you. Except, obviously, product rule and chain rule and stuff. You should know those things. Quotient rule, we don't give you those. But geometric shapes, we'll give you those formulas. Although, I don't know, there should be a limit. If it's just a rectangle, should you have to be given length times width? I don't know. That one you ought to know. I think we can expect that one. But three-dimensional objects, I would think we'll give you formulas for. Does anybody remember what a cone looks like? Well, obviously a cone, what it looks like. I'm sure everybody knows what it looks like. Do you remember what the formula looks like? Those are supposed to be straight lines. Oh, you're thinking, you know what? You've got it mixed up with a sphere. You're thinking sphere. No, it's only 1/3. The volume is, and this is interesting. Think back to what the volume of a cylinder was. It was just pi r squared h, area of the circle times how tall it is. A cone takes up exactly 1/3 of the volume that a cylinder would if it had the same shaped base. So it's 1/3 pi r squared h. All right, we're getting ahead of ourselves though. Let's take a look at our data. What do we know here? Well, we know from this thing, the givens that we are told are, we're told that the volume this time is changing at a rate of 5 cubic meters per second. And what we'd like to know is we'd like to know dH by dt, right? We want to know how fast is the water level rising. And again, that won't be a constant, because think about it. If I'm pouring the water in at a constant rate of amount of water going in, that height will go faster. Sorry, that height will increase really fast at the beginning, and then it'll slow down, right? So I want this at the point where, let's see, at the point where the depth of the water is 4 meters. So the volume's not the volume, sorry, the height. The height is 4 meters. And the radius I don't know. Okay, I do know the entire cone though. Maybe I'll just put that on the diagram. For the entire cone, this radius here is 2 meters, radius at the top. And this height is 7 meters. So think about it this way. I kind of have a second cone here when the water level is up to 4 meters. It will have a radius of its own from there, but I don't know what that radius is, so I'll just call that r for now. So how am I going to find that r? This is where similar triangles comes in. Can you see that in this diagram I have let me use a highlighter again. I have a large right triangle here. And I have a small right triangle here. And those two triangles are what we call similar. They're not congruent, they're not identical, because obviously one's way bigger than the other, but they have exactly the same angles, which means they have exactly the same proportions. And if two things are proportional, that means their ratios are the same. That means that I can, here, I'll redraw them. So I'll stick to the same colors. So the big triangle, and again, it's a right triangle, right? There's, you say, radius would obviously make a right angle to the height. So the big triangle is 2 by 7 that way, and the little triangle, which is exactly the same shape, just smaller, is 4 by some radius that I don't know. And I can draw two conclusions from this that are central to me being able to solve this problem. Does anybody know how the math on this works? You literally just set it up as two ratios. You know that the proportionality of the blue triangle has to be the same as the yellow. So you can say that 2 over 7 has to equal r over 4. So I can make one conclusion here that is very important to the problem. I can say that when my height is 4, my radius is cross multiply, or times both sides of the equation by 4. My radius is 8/7. So there. I've solved for one of my unknown givens. Just as important, though, since I am told that the water is flowing into the tank at a constant rate, this proportionality would be the same for any water level. So I can say that the derivative of the radius with respect to time will always be this proportion of 2/7 times the derivative of the height with respect to time. So that 2/7 proportion holds everywhere on here because the water is flowing at a constant rate. So now let's go to our actual equation again. Let me kind of start it over here. Volume equals 1/3 pi r squared h. And let's do the derivative of it. So we are taking the derivative with respect to time of all three of those variables. All right, well, I'm chain ruling all of them. V is just to the power of 1, so that's dv by dt, which is actually something I'm given, right? 1/3 and pi are both just coefficients, so I can just kind of ignore them and stick them out front. And then I have to do, again, the chain rule on r squared h. And we've kind of already seen that. It's going to work the same way it did in the last example. So I'll run through it again. The derivative of r squared is 2r dr by dt times the other variable. Plus, now I want the first thing, the r squared, times the derivative of the second variable, which is dh by dt. And there is only one thing in here that I don't know. And that's the thing I was looking for. I don't know dh by dt. You might be thinking, well, you don't know dr by dt either. Yeah, but I can express it in terms of dh dt because of that similar triangle proportionality. So let's replace it. Why won't that go away? Excuse me, sorry. All right, so let's put in all the numbers now. They told us at the beginning, actually, I'm writing really big. I'll move to the next page here. So I'm going to start replace. Here, I'll run through all the givens again. Remember that we were told that the volume is changing as a rate of time at 5 meters cubed per second. We know that the radius right now is 8/7. We know that the height is 4, and we're looking for dr dt, but we know that dh by dt I've got that backwards. We're looking for dh by dt, but we know that dr by dt is 2/7 times dh by dt. So we can take all 4 of those variables and substitute them out. So the left-hand side of the equation becomes this 5, 1/3 pi. The 2 times r can become 2 times 8/7. dr by dh can be replaced by 2/7 dh by dt. And then we still have an h. This time I won't forget it. Plus, and the r can be replaced by 8/7. And dh by dt is the sole variable that we're still looking for, right? That was the whole question that we were being asked. How fast is the water level rising? Okay, I has a question. What do you got? Yes, thank you. I lost a squared. Any other questions on how I got to this far? Okay, after this, it's just arithmetic and algebra. The numbers aren't very pretty on this one, but we'll just kind of work with them as best we can here. So let's see, that's 1/3 pi. And okay, so we have 2 times 8 times, hang on, did I forget a variable again? I think I did. 2 times r times, oh, yeah, I forgot to change this h to a 4, because I know that the height is 4. I don't know why I left that as an h, my bad. All right, now let's put all the numbers together. 2 times 8 times 2 times 4, so that's 8 times 8 times 2, so that's 64 times 2. So that's 128 over 7 times 7 times dh by dt. I guess I should keep this in a big square bracket. Plus 8/7 squared is 64/49 times dh by dt. Okay, I think I'll factor out the dh by dt. Leaving behind 128/49 plus 64/49. And let's do the arithmetic carefully. I've been making all kinds of little goof-ups this morning. What is 128 plus 64? That's 192. Somebody double check my mental math. It's been that kind of morning. 192 over 49, I think, is right. dH dt. Okay, so basically, my final answer will be 5 divided by all of this. And at this point, I just go to my calculator. Although 3 does go into 192, I could simplify it that way. Right? But it's okay. I think I'd just punch buttons at this point. So let's see. Let's see if I get the same answer I got when I did this yesterday. 5 divided by, open a bracket, 1/3 times pi times 192 over 49, close my bracket and hit equals. Yep, same number. And it's a fairly reasonable number. 1.22 meters per second is how fast the height is changing. At the 4 meter mark. Obviously, again, it's changing at a different rate as you go. Once again, I have an animation for this. Let me get my animation going here. Actually, I have several animations. Check this out. First of all, here's the change in the cone if the change in volume is a constant, which is what we have, right? Change in volume is constant. And here's what it would look like if it was the height was changing at a constant rate. And you could compare those two side by side here. Let's see if this works. They're not going to make us watch an ad, are they? Okay, there we go. So again, what's the difference here? The one on the left, the height of the water is the constant change. And on the right, the volume being dumped into it is the constant change. Notice there is a difference there, right? Okay, that's about as far as I wanted to get to today. I'll just stop the video.